All right, welcome to week 16, day one. Today we're going to talk about some basics of, here it says machine learning. It's actually a little bit more of the basics. It's like a very high touch the surface of actual neural networks. I'm not sure if you guys are quite ready for this, to be honest, but it's in the curriculum. So we're just going to touch on it. I will encourage for each of you, if you do find it interesting, definitely deep dive because we're just kind of touching on topics that I feel like you guys have no business knowing yet, or probably shouldn't know for like years, but it's okay. You guys are very advanced, and I'm not really too concerned about it. What we're gonna do for our lessons today is I'm just gonna kind of talk you through some concepts and stuff. For the lab and the assignment, I'm actually gonna split you guys into teams. You're gonna work on the lab together. It's all there. It should work. If not, have fun debugging. And then for the assignment, since you guys appreciated last week that you had some I don't know, I could think you had more like leeway. What you can do today for your assignment, and it's all written out here, you're essentially just gonna break it if you want, just kind of like really play with it and see how things are affecting things because whenever you're dealing with neural networks, it's actually just about that. It's about weights and balances. So that's what you're gonna do today. And then everything is going to be local, so you can always reproduce this. And you don't have to worry about cost if you want to do this on your own. So some of the objectives and some of the things we're going to just touch on. And you're going to understand fundamental difference between traditional programming, machine learning. We're going to talk about PyTorch a little bit, some structures. We'll skip this overview. Why should you care about machine learning? I think a lot of times we think about it from a customer perspective and we just think of like chatbots and stuff. But it's like, why should you care about it? Like, what are some of the other things? Here, you can use it for prediction. And then this is also a customer-based one. So it's like, oh, what song the user's going to listen to? Yeah. But you remember, you could predict anything. You have creative outlet to say, hey, how, as an engineer, how can that help you if you want to build your own internal tools? You can use it to detect if an uploaded image contains inappropriate content, right, for moderation. So this is like, I know a few weeks ago, I think we just mentioned convolutional neural networks in the sense of, images, so you can utilize detection. You already know that it can generate personal product recommendations, it can generate anything. These examples aren't that great, but you guys get the gist of why, what it can do. But for machine learning, right, reason you should care is because without machine learning, you cannot do any of this. It's kind of as simple as that, and it kind of comes down to what you know currently, like what we've taught you versus what can be done. Because what you know is called imperative programming. Imperative programming is literally you telling the computer what to do. So, you're very familiar with this. An example is like an if statement. If a user subscribed and they're on a premium plan, show them the content, right? We said exactly what to do. And that's because we can account for the potential options, right? In the scenario, we could say, hey, are you not subscribed, right? We know there's a user, they know they have a subscribed state, they have a account type, whatever, right? We know what the options are. So fine, that's where imperative programming comes in. But then there's machine learning. With machine learning, you don't tell it what to do. You define a goal and you provide data. So then the computer has to figure out the relationship. This part right here, I don't want to undersell this. The computer figures out the relationship. That's like literally machine learning. That's like not all it's doing. That's the objective of what it's always doing. And as you learn about neural networks and as you learn about just any sort of like training, training models with the output, it's literally just about capturing what the relationship is and how accurate those relationships are. So here it's just a machine learning pattern, if you'd like. And then you'll notice like how little of code it is, but it's model.train. So you know this is a function. And we're going to pass in the data. So it's like, we're going to give you data, train on this, right? And then it's going to utilize it for prediction, right? Or applying learning patterns. This right here, once again, not to undersell this, but this is literally what machine learning is right here. Um, we're not going to do it today. There's a whole universe of what you can learn regarding that, but that's what machine learning is. So you don't write logic, the model discovers it. Once again, it figures out relationships. So then a learning model is essentially complex mathematical function that has been tuned. So be adjustments of weights and balances, has been tuned to recognize patterns in data. I know I haven't said much. Does anyone have a question so far? Okay. So then there's, for today, we're kind of jumping around here, but just for today, or I guess whenever you're working with machine learning, just know that your developer environment is very important, your virtual environment. Now, there's other times where it's like nice to have. This is one of those times where it's like, if you're going to touch it, make sure you have a virtual environment. Here it says just like JavaScript has node modules, Python uses virtual environments. We can skip that portion. The TLDR on this is that, like, especially if you're using Tensor, which we're going to touch today, it has over, I think, like, oh, it's actually in here. Oh, yeah, right here, PyTorch. So PyTorch and its dependencies are massive. There's several gigabytes. So if you're just installing this like on your computer, you know, it's not really good for business, if you would, especially when utilizing other projects in the future. So ensure that you do have virtual environment. It's more important working with this than it would be. Here's a setup, but you guys already know how to do this, right? Virtual environments, but here's the code if you need a reference. One of the cool things when you're doing machine learning, it's heavily advised that you utilize Jupyter notebooks. Jupyter notebooks is something that you can use. Like if you guys are using AWS projects, you can utilize Jupyter notebooks through AWS. However, there is a local version that you could do right in your VS Code or whatever IDE that you have, utilizing this file extension. So instead of like .py, you can do .jpynb, Jupyter Notebook, and you have all the power of the Jupyter Notebook, but right there in your, not in your terminal, excuse me, right there in your IDE. So Jupyter is the industry standard for data science. And machine learning is data science. So don't be confused. It absolutely is data science. So unlike a standard .py script that runs top to bottom and then exit, right? So if you run a code, it goes line 0 to line X, and then it says, okay, cool, I'm done. Jupyter actually keeps Python alive. It's going to just keep running. So with that, you get some benefits. There's three big ones: persistence, interactive, and exploratory. With persistence, let's say you load 1 gigabyte of data, because remember, right, for like our example here, if you want to train something, you'll feed it the data. Okay, cool, step 1. If it's a whole gig, let's say, of data, and you run like your, not your script, but your notebook, right? Cool, how long is that going to take? Probably a while. Now, let's say you finish doing what you want to do, and then you say, oh, you know what, actually, I want to spin up that function again. Do you want to load that 1 gig? No, so like that's a big benefit of using Jupyter for machine learning, which once again is actually data science. You're going to work with a lot of data. So here you can load the gig once and it'll just stay in the memory. And then you can test different code without reloading. It's also interactive. So whenever, with Jupyter, you do have, and you guys will see this, you know, as you build it, but like, with Jupyter, you can think of it as like kind of like text field blocks, if you would, and you're literally just going to enter in code and run it. You don't have to run the whole Jupyter file, and that's what's really cool about it. You're just running segments, which is really good for testing and isolation. But here, you can use it to generate tables, charts, errors. So it's going to actually create outputs for you as well. It's not just a notebook in that sense. It generates. Exploratory, it's perfect for experimentation. And this is because you can run cells in any order. Like I said, you have these cells where you put your code in, and you don't have to run that whole file. You'll run specifically what you want, when you want. So it's really good, especially when you're like tweaking stuff and playing with things. So you can think of it like running a dev server. It's not, but think of it like running a dev server that never shuts down. Each cell is like a route you can hit whenever you want. And then I just wonder if we can just get an image real quick, just so you can see what these cells look like. It's literally like this. These little, like I said, they're kind of like text fields, but they're not. You can actually put in a function and run it. A PyTorch function, whatever you want, it'll actually generate it. So we're going to mention tensors briefly. We're not going to deep dive into any of this stuff today. It's mostly just about to get you to the lab so you guys can really just like get your hands dirty, and these concepts will be more clear. And not clear in the sense of, oh, hey, I'm a machine learning expert, but clear in the sense of saying, oh, I can utilize machine learning to build, right? Because it's a boot camp, not a like university structure. But the tensor, right? Machine learning's universal data structure. So machine learning doesn't know what strings or objects are. It only speaks tensors. So what's a tensor? It's a multi-dimensional array optimized for high-speed math. Remember, it's data science. So if you're not familiar, we're going to mention it right here in a moment. So if you say, like, I think everyone here should know what an array is. A multi-dimensional array is essentially arrays within an array. There's examples at the bottom. My apologies. The thing that's important to understand is there's also a concept called rank. It could also be called dimensions. It tells us how many directions the data moves in. But if that doesn't make sense, it should make sense right now. So rank 0, remember, we have ranks. Scalar, or scalar, depending on how you say it. It's a single value. So if you were to write let x equals 10, we should all agree this is a single value. It's just really x, one line of code. So machine learning uses a loss score. It's a little advanced, but it's a single number representing how wrong the model prediction was. Remember, if we said it earlier, machine learning is about relationships, right? Like prediction of relationships. So a loss score is that. It's like how wrong is its prediction of a relationship to what it should actually be. Remember, these are just concepts. Don't worry if you don't understand exactly how that works, because we're not going to like deep dive into this. But here's an example. Well, for this example, I wonder if we can explain this example without deep diving. Here's what I'm going to tell you. For this example, it's just saying that we're going to import Torch, obviously, utilizing tensor, and then we're printing out this scalar shape. But I don't think that's going to make sense without us running it. So for now, let's focus more on these ranks. So for rank 0, you already know what a scalar is, which is a single value. Then a vector is, remember, it's actually just a single array. And if you go back, right, we had mentioned that a tensor is multi-dimensional arrays, right? So we have another rank, rank 2, which is a matrix. Don't get confused with the movie, unless you'd like to. But a matrix, or rank 2, is literally arrays in arrays. So here, right, you have your one array, right? And then inside it, you have 2 arrays. Before I jump ahead, does the concept of the rank from single array and a matrix make sense, just in the sense of what they are? Or is anyone confused by the matrix itself? Okay, cool. The reason why it's important to know is because in a moment we're going to see an output of a multi-dimensional when we get to the code example. But the next rank is, I don't know why these have links. The next rank is a 3D tensor, known as a stack. So you can think of it as a stack of spreadsheets. And then here, machine learning use would be for images. So if you're thinking of a grid of pixels, which would be a matrix, right? Arrays in an array, a grid of pixels. But now it's stacked 3 times, one for red, one for green, one for blue. You now have a 3D tensor, which is utilized for images. Does that make sense, at least conceptually? So a grid of pixels would be a matrix, but the grid of pixels would be stacked 3 times, so each stack would correlate to its own color. Red, green, and blue channels, which are the colors utilized to create all colors and within pixels. Does that conceptually make sense? I got half a head nod from two people. I want to say that equals one head nod. Okay, so yeah, it's just a concept. Not to say it's not a tangible thing, because you can code it and print it, but for now, as far as we need to know, it's just a concept. Okay, so then why PyTorch tensors? Why not just use list? And that's just because everything in coding is kind of like everything else, right? It's how you utilize it. So you could try to make the argument to say, oh, we can potentially use Python lists to mimic what we're describing and create arrays within arrays and such. But one is going to be memory management. That's a huge difference. So tensors are stored in contiguous memory. So that's right next to the RAM. This is within the actual, now we're going like, like lower level. This is much faster than the CPU to read than a Python list. So that's memory management is a huge reason, because we're going to work with, if you're working with PyTorch normally, and tensors, you're working with large data sets within the realm of machine learning. Then there's GPU acceleration. If you guys know about data centers, right, you should know how important GPU is. Tensors can be moved to graphic cards. So then the graphic, you can't do that with a regular Python list. And then while a CPU does one calculation at a time very quickly, a GPU can do thousands of simple calculations simultaneously, like matrix multiplications, right? So the matrix, it's arrays within arrays. Each one of those can have its own calculations, and the GPU is like, no problem, here you go. And once again, that goes back to the memory of where it's stored. And then automatic differentiation, you can call this the magic if you'd like. It's the most important part, magic. So tensor tracks every operation performed on themselves. That's what it should say here, not on them. When the model makes a mistake, PyTorch can walk backwards through the math and figure out which weight needs to be adjusted. At the moment, we haven't touched on weights and their importance, but when we do, just know that PyTorch can go backwards and redo the math to adjust it. We'll touch on weights in a moment. Actually, with this, let me see, because we talk about weights and parameters in the next lesson. I'm wondering if it makes more sense to mention it now. I guess this one's almost done. We'll just kind of power through this and see if everything comes together at the end. Okay, so then essential tensor operations. We can practice the fundamental operations you use every day. I do also have a cheat sheet. I don't know if these are the same though. Let's see what we got here. Okay, this is more important than this portion. Well, not really, because it's all important because this is that. So here you could already see that we do have a matrix. Here we also have a function called random, R-A-N-D. Just know that although it's random, it's not going to generate a random number in that sense. It's going to generate a random value between 0 and 1. And that's actually the basis of like probably every random generator. It doesn't actually generate a random number. It normally generates a random value to 0, 1, and then manipulates it to become a random number, or to become whatever number multiplied to give you different values. But anyway, here you'll notice though, this is specifically through Torch. So we have 3 and 4. So when we're asking rand 3, 4, we're not saying, oh, give us a random number, right? That's 3 and 4. What we're saying is give us a matrix that is going to be, and you'll notice here, all of this is within one array. So here, what it's doing, it's 3 arrays. That's the 3. Each array has 4 values. That's what this is. So it's a 3 by 4 matrix. If that portion makes sense, we can move on. Because like I said, this is just random matrix 3 by 4. Does that at least conceptually make sense? Like if you had to, type this in. Okay, cool. And then zeros or ones, great for mask. Let's skip that for now. I don't think it should be in here either. Inspecting tensors. 90% of debugging in machine learning is shape mismatches. The shape is essentially like this output, like when you refer to shapes, within data science or machine learning, you're literally referring to the shape of the data. So, for example, like you can say that this is a shape here, right? This is a matrix shape, like 3 by 4. So in this sense, let's see here. What is this doing? Oh, okay. I guess so here it's saying if you're specifically printing whatever dot shape, it'll give you like 2 by 2. So in this example, it would be 2 rows, each array. Each of the 2 arrays would have 2 values in it. It's saying you can do it by type. Say, oh, it's a float, it's a num, it's whatever. You can do it by device, where it lives, CPU or the CUDA, the Barracuda, if you would. And then it can also do basic math. Here you go. Min, mean, sum, argument. Like I said, this is just a little bit more of a cheat sheet that you can utilize. So if it doesn't make sense now, that's fine. But as you're playing with the lab later, you can come back and reference this. Here it says hand-on practice, but we're going to skip this for now. Like I said, it's just more about showing you this to get you to the lab. Okay, so here, I've been talking a lot. Can someone just read this and then we'll kind of move on here. Mental model summary, the big picture.
Here's the big picture. Data
Ooh,
to tensors.
never
Everything
mind.
in machine learning must be converted to numbers in multi-dimensional arrays. Tensors to models. The model is a function that transforms tensors. Model to predictions. Output tensors represent predictions. Wrong predictions to adjusted weights. Backpropagation updates the model.
Okay, cool. So yeah, so this is essentially an overview of it. And like I said, right now, I'm not expecting all of this to make sense. I'm expecting for it, I'm expecting for this to just be something that lives in your brain, just for now. Because like I said, once we get to the lab, then the concepts shouldn't feel so foreign, and they should feel like, okay, yeah, we touched on this, and it should just kind of like clear it out for you. Common pitfalls and solutions. If you can't, we're not gonna go over this. If you guys run into pitfalls or need those references when you're doing your lab, you can just come back to the end of this lesson. I do have some sources here for you. Let me move you guys out of the way. We do have PyTorch documentation and tensor shape visuals. So yeah, here if you guys go to the playground, you can actually create different shapes. It's different data. So this should be fun for you guys. If you guys need to do this before like the lab, like if you guys kind of want to just like more hands-on, go for it. If you want to wait till later just to like as an extra thing for yourself, I would recommend it because the more you play with visualizers, the easier it is to digest the math portions as you do them later. Wait, where are we at right now? Okay. So that's the first portion. What time? Okay, 30 minutes, cool. And I don't know why this isn't loading. Or am I tripping? Unless I overwrote it. Oh, no, it's straight up not working. I wonder why. Okay, that was weird. Okay, so now we're going to just talk about neural networks a little bit. And this is going to be as abstract without the, without proper foundation. But like I said, hopefully this all comes together for the lab. We don't need a recap, you guys. So reshaping tensors, preparing data for neural networks. Neural networks are picky. They expect data in specific shapes. If you're feeding an image classifier, it doesn't want 28 by 28 grid. It wants a flat 784 element vector. It's just an example. So the problem, let's say you had a 2D image that was 28 by 28 pixels. Remember, here we essentially a matrix. So if we had 28 by 28, there's your torch size. We already know the shape, it's 28 by 28. But then your neural network expects a singular, a 1D vector. Then how would you do that? Right here, you would create a flat image if you would. So you would use, and there's already something built in, which is why you guys don't have to like really know like everything to build. You should know it in time, but for now. You can use image.reshape as a function, and you can give it that 784, and then it'll create the flat image shape. And then Y784. Well, actually, I guess that's good. Yeah, if you guys didn't catch that, 28 by 28 is 784. So it just, instead of having a matrix and array of arrays, now it's a flat singular version, right? Or the that rank one based off of what we were talking about earlier, where it's like single line, single array, matrix, and then the 3D stack. There's another thing here called unsqueeze, adding a batch dimension. Neural networks process data in batches, multiple examples at once, if you remember, because it rocks on the GPU. So even if you have one image, you still need a batch dimensions, because remember, one image in this case would be a matrix array of those pixels. So here, a single image, 784. You can utilize this, the RAND 784, and then a batch single unsqueeze, and then your torch size would now be 1, and then 784. I don't remember how involved that is with your lab today. I think it's just more of an example. But in real world, training processes, whether it's 32, 64, 128 images at once, your tensor shape becomes the batch size and the features. Batch size, we wanted 1, and the features are 784 of them. I feel like we're throwing a lot. And then let's say we did a squeeze function, removing unnecessary dimensions. This should be the opposite, but after predictions, you might get a tensor with extra dimensions you don't need. So here, if your model shape is 1 and 10, right? Single, or yeah, size in the arrays, one batch, 10 classes, then your output, you can torch.rand it, and then you would remove the batch dimensions. So then here you're going to squeeze it, and then you would just get that 10. Essentially, it's kind of like pruning, but no, it is like pruning, but I feel like then we're going to open up a whole new rabbit hole. So let's just keep rocking and trust the system here. You can stack tensors. So combining multiple tensors in a batch, literally image 1, image 2, image 3. But then here you would just stack them using a stack function. And then the batch.shape right here, it would actually be 3. Remember, we now have those the 3 in the batch, and then the 784 is that the value. So understanding neural networks. Okay, so check this out. As of right now, like I said, this kind of all feels random. Like, why are we talking about relationships, and why are we feeding in things and getting outputs, and why are we even feeding it an array to begin with, right? It kind of hasn't touched on that. Here's the concept where it should come together. There's something called a neural network, which is this. This is obviously not it. It's not literal. It's let's get an image of this. I just wanted to get the image. So there's something called a neural network. This is what machine learning actually really is. You have different layers. So you have an input layer, right? Remember, we were just kind of inputting stuff into these functions, right? You have these hidden layers, and you have an output layer. Now, as long as you have 2 or more hidden layers, that's technically deep learning. Modern day deep learning have like thousands of hidden layers, but essentially what's happening is it will get the data. There's a system of weights and balances that's it's all math. So it's like doing math, bloop, 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 right? With the sounds, and then it's getting an output. There's different types of functions that measure your error. It's like error, like means error and just error loss of this output. And essentially what happens is then there's a comparison of saying, hey, how close, what's the relationship of this output compared to what it's supposed to be? And if it's not close, what it does is it goes back through. It adjusts the weights and balances, which for now we're not going to deep dive into, but it's literally random numbers. Like it starts out as random numbers. And you adjust these random numbers and run it through again and say, hey, are we closer? Okay, cool, we're closer, but not close enough. And it's going to kind of keep doing this process until you get an output that's satisfactory. And then you say, okay, cool, now our output has a close relationship. It has a minimal loss because there's always going to be some sort of error. So it has a minimal error compared to what we wanted. Let's keep this. This is now our model. That's how models are made. So this is to make it just a touch less abstract, but understanding neural network. So a neural network, as you can visualize, it's a function of composed layers. Each layer transforms the input, passing it forward until you get a prediction. And I just can't emphasize this enough. The more you start getting into like AI, it's literally predictions that are, it's predicting relationships and measured against what it should be. And it's either right or it's wrong. And literally, it's just, once again, going to be just slightly modified one way or another to say which way's more right or wrong. And it's just going to keep predicting until, you know, with those adjustments until you get close enough. It's really weird, but when you start learning it, it's pretty trippy and crazy that this is like running our world. But anyway, so the architecture, you have your input layer, your hidden layers, and your output layer, which I showed you in that diagram. So example, classifying handwritten digits, let's say 0 through 9. Here, you would send in these pixels. They would go into the neurons, and then you would get this output of 10 classes. So it's supposed to be like the input hidden layers, plural, and then the output layer, these 10 classes. So how it works, each neuron in a layer, it's a, wait, where are we at? Excuse me. Each neuron in a layer performs these weighted sum and add bias and apply activation function. So with the weighted sum, it's you multiply each input by a weight. Remember I said random numbers? Literally, the weight is a random number. So the weighted sum is going to be multiplied by it's going to multiply each input by a weight. And then you're going to add a bias to offset the result. And that's because, remember, your result's going to be a prediction. And if it has too much error, you need to offset it. And then apply activation function, which introduces nonlinearity. To understand this, we would have to talk about the different types of functions that are involved. They're all different math formulas, and it wouldn't be appropriate to get into because that's a whole nother class. So just for now, just know this is the concept of how the neural networks work. Yeah, okay. Yeah, no, this is kind of cool. So the output, remember the output layer? What is it actually? It's the weights timed inputs, or excuse me, not time. I'm getting old. The weights at the inputs plus the bias. That's essentially the activation. That's the output. So weights and biases. Weights, how important each input is. This was learned during training. The bias, offset values that help the model fit better. They're also learned. The activation function. So without activation functions, a neural network is just a linear function, right? It's a straight line. Oh, it says it there. It's like a straight line. So in activation functions, let the network learn complex curved patterns, opposed to just linear patterns. Common activation functions. Let me see what it actually shows here, Rella. Oh, cool. So I didn't know this was in here. So yeah, so like I said, we shouldn't really get into it, but here, these are different types of functions here, of the activation functions. They're all math, is what they are. So there's ReLU, the rectified linear unit. This one's, it is the most common. This is like the classic granddaddy, if you would, of machine learning functions. So this one, what it does is it turns negative values to 0, and keeps positive values. I don't see why this would make sense to you. Here's what I will say. There are these different functions. Each of these functions help control these, within the hidden layer, they help control what the output's going to be. But what happens is, like, within this neural, I keep clicking on it, within this neural network, if things turn to 0, they're essentially dead because they're only going from 0 to 1. They're essentially dead. So if they're negative, it doesn't help. So here it kind of just, it turns it to 0. I don't know if there's the best way to explain it. Yeah, like I said, I wouldn't. I I don't know why this is here, guys. All right, here's the thing. Um, Let me think of a simplified way to share this where there's still some value within this portion. Um, Essentially, this whole process of neural networks is math. Everything has an output. Along the way, you have those hidden values, this hidden layers. Um, the thing is, based on these training models, sometimes things get trained too well. Um, and sometimes they get trained too well, and sometimes they're not trained at all. But there's a problem with that. If something's trained too well, you would say it's overfitted. And the problem with that is it learns the training material so well that if you give it a new question or a new example, I mean, whatever it's doing, it's not going to know the answer because it's literally trained too well on the data. And then if it goes the other way, it kind of has that opposite problem where now it like doesn't know anything, right? So you got to find that right point. And essentially, each of these activation functions, they all have different methodologies of creating that output. They all have different ways of fighting, if you would, how like fighting over fitting and fighting under fitting. And I don't think that explaining them in more depth is going to help you guys at this point in your journey. Um, but just know that's what they're there for. They're just different methodologies to get a result that should be the most appropriate result. That's different based off of your cases. So building your first neural network, because today you guys are going to create a neural network. That's why we're just kind of roughing going over these concepts. So here it says define the network architecture. And let me see. We're going to skip this because you are going to do this in the lab. In the lab, hold your hand through it. But just know that you do have to define the network architecture. And then you do have to test the network, the forward pass. The forward pass is literally, whenever anyone's referring to forward pass, it's literally just a process from input to output. And then if anyone refers to back propagation, it's adjusting those weights and biases, right? Everything in the hidden layer, the functions and everything, it's doing it again to get a different output. So it's forward pass and then back propagation. What is a little bit more important is this, hyperparameters versus parameters, because when you're talking about forward propagation, it utilizes the weights and balances. When you're talking about back propagation, doing it again, it's the adjustment of these parameters. So what these parameters are, the actual values that the model learns during training. And then who sets them? The model automatically updates these via back propagation, which is where it's going through it again. The initial values, when you first start, the weights and balances are usually random. And by usually, it's like 99% of the time, they're going to be random. And then it's up to the AI. It learns which direction to change these values in up or down using specific initialization strategies. And then an example, let's say there's a weight of 0.73. Don't get confused. Remember, that's just a random, it's just random. So the weight 0.73 that connects neuron 5 in layer 1 to neuron 12 in layer 2. I mean, that's a little confusing here, but essentially what it's saying is like here, let's say there's this and like say there's that one, right? You see how there's all these lines? That's what it's just referring to. It's just saying the weight for these two specific neurons in this case happens to be 0.73, which is like establishing some sort of like it could be like in a sense like a relationship between the two, the weight of importance between those two. So these are the knowledge the model gains from seeing data, because then it's going to know to adjust that or potentially adjust that once it back propagates, once it goes through it again. But there's two important classifications. There's parameters and hyperparameters. So remember, these parameters can be adjusted during the training phase. Hyperparameters, these are settings that you configure before the training starts. So who sees them? You, the developer and the data science. And they control how the training process works, not what's learned. So just know that hyperparameters is what you're setting. It's like a config. And then the parameters is what can be adjusted for training to get the optimal result. And those are random and then changed by the AI as it learns. And then common hyperparameters, if you've asked, like, hey, what are we configuring? You can configure the learning rate, batch size, number of epochs, the architecture choices, and the optimizer types. Today, you are going to set these in probably random, or I don't remember if they're pre-labeled for you to just pop in, but the learning rate is actually, does somebody want to read this portion? These are common hyperparameters.
Sure. Learning rate, how big of a step to take when updating your weights. So learning rate equals 0.001. Sorry, I lost my glasses, so I will be squinting. Batch size, how many examples to process at once? As an example, 64 in that instance. Number of epochs, how many times to iterate through the full data set. Architecture choices, number of layers, neurons per layer, optimizer type, which algorithm to use for updates. So that's going to be like Atom, SGD, or RMS prop.
Cool. Yeah, so pretty much everything in the sense of like you can kind of think of it as like a lab. Like if you were conducting your own like research like a lab and you're setting the hyperparameter, you're setting the configuration of how this lab's going to be ran and how it's going to operate. That's what you're predetermining. And then everything else is up to the AI to adjust to get the optimal result. A cooking analogy, let's hope this is pretty good. You could think of training a model like baking a cake. Let's say hyperparameters. Remember, this is what you're setting. The oven temperature, we're going to do 350 degrees. The baking time, 30 minutes. The pan size, all right, 12 inches. But then the parameters would be how well cooked the cake becomes. This is learned through the baking process. I mean, I guess if it was like an AI oven, I think that's fair to say. Maybe the wording could be cleared up. But if it was an AI oven, yeah, let's say we set the parameters and then how well cooked the cake becomes. I don't know. I'm not feeling that analogy. How do you guys think that's good? Should we keep that in here or delete that for the next cohort?
Maybe the physical and chemical changes that the actual ingredients undergo while being baked. I don't know.
Okay.
I feel like that's almost as weak.
Yeah, me too. But you shot your shot and you're trying to help this terrible analogy, so that's good. Well, then let me ask this. Does anyone have a better analogy then? Forget the cooking analogy. Um, does anyone have a better analogy for the parameters and hyperparameters?
Other than cooking?
Yeah, yeah, one that actually is good because
I
the cooking
mean,
is terrible.
for cooking, I would maybe, if you're gonna go with the cooking analogy, I would maybe say like it's the different spices that you could use to like make an optimal dish. I don't know. Because
Okay.
depending how you put your your different ingredients in there, like your different spices, like it can create a different result. I don't know. I think I might,
All right. All
yeah.
right. Anyone else have a potential analogy for hyperparameters and parameters?
The
That
student
like,
analogy.
okay, that's
Parameters are the knowledge the student learns during class and study time. Hyperparameters are the external conditions and study strategies set by the teacher or student beforehand.
so what's really cool is that's the one that I literally just thought of, but the way you said it, it sounds like you're reading it.
It
I
does.
am.
I was going to say, did you ask a GPT?
Hell yeah, I did.
Of
Oh, well
course.
then I'm as smart as AI. I'm as smart as random math.
Hmm.
All right. Well, that's good. Yeah, that's exactly what I was thinking. Like kind of like the classroom is the hyperparameters. Say, oh, the lecture's this duration, et cetera, et cetera. But the only reason I didn't say that, because I am smarter than an AI, is because that's kind of like too on the nose in a sense. Because neural networks are set up in a sense to resemble how neurons work in our brain. So now we're just saying instead of saying neurons directly, we're saying, oh, the human, right? The human containing the brain containing the neurons. All right, but it sounds like the good thing is, even though a lot of this information is a little rough, I think, to digest, it sounds like everyone at least understands parameters and hyperparameters. So, like I said in the beginning, I believe in you guys. You know, even if these concepts are like way above where I think this was probably introduced too early in the course for me personally, but I mean, you guys are just unstoppable, man. So I'm proud of you. All right. So then the training loop, how models learn. Training a neural network has 4 steps, repeated thousands of times. Forward pass, I kind of already mentioned this. Feeds data through the network, right? That's just going through literally going through this once. It's called the forward pass. Then there's calculate loss. You have to measure how wrong the predictions are. And that's like, it's literally what it is. I just can't emphasize this enough. It's always going to be wrong. You're just trying to minimize the wrong. And then you say, okay, that's good enough. All right, then there's backward pass, which also back propagation. This is calculates gradients, how to adjust the weights. So it says, okay, how do I update them? And then it says, okay, based on how I'm going to do it, now I am going to do it. And okay, yeah, that's the backward pass. And then it does back propagation and goes through it again. So literally, it just repeats this nonstop until it's done. The thing is, part of what you can set, like the epochs is how many times it does this. I don't think that was clear up here. But how many times it goes through that process. So what's really cool too is as an engineer or a data scientist, you can choose a lot of parameters. So like if you have a targeted output, you can say, oh, if it hits this target, which usually you wouldn't, right? Because you normally don't know the target. Well, actually you do know the target, so I guess that's inaccurate. But pretty much like, let's say the error, you have a certain percentage of error. You can say, hey, stop when you hit this certain percentage of error. You can say stop after this many epochs, and then you can also say, yeah, I guess just stop if you get it. And if not, it can technically, oh, no, I'm sorry. The third one I was thinking of is, let's say each time it's getting closer and closer, at some point you get what's called diminishing returns, which is like, okay, yeah, I am closer, but it's like so marginal. It doesn't really matter. It's like, what are you going to do? It's 100 bazillion more times, and maybe you're going to get closer. So it's kind of like, you can map the results, right? And then whenever it starts to plateau, you can just cut it and say, hey, this is the best we're going to get. So yeah, those are the three things. It's based off of how much better it's getting, right? If it plateaus. Yeah, Troy.
Can you talk a little bit about overtraining?
Sure. What do you want to know?
Well, just in terms of what you were describing as you were going through the loops and then it stops like showing diminishing returns. Isn't that a point where we've overtrained our data?
Diminishing returns? Is it overtraining data? Oh, because overtraining data, no, it can't be. Because when you overtrain your data, it's literally like it doesn't know anything but the data, like not even closely related stuff. For example, like the classic is like the image of the cat, right? It wants to know if it's a cat or if it's a dog or just whatever. Imagine that your model got 100% correct. And like we said, there's always going to be error. It's predictions. So let's say it got 100% correct. Okay, cool. On the training data. Now I just send it a picture of my cat. And it's like, I don't know, what is that, a dog? And I'm like, I thought you knew cats. You got 100. But it doesn't know cats. It knows those specific pictures. That's what overfitting is. It just knows that training data. So in your question, you're saying if it's too good, does it correlate with it overfitting? I guess I want to say possibly. I think possibly is the right answer. Would anyone, Mike or Kim, have input on that if you know for sure?
I would think overfitting is almost like over engineering it to where, like what you said, Jonathan, it's like a diminishing return, right? Because eventually when you do overtrain, you're gonna lead to overfitting for that specific training set. That's kind of how I look at it.
Okay. I did write this article if you guys would like to read it. I don't know if it's going to help or hurt. But
Jonathan.
I wrote, excuse me? You said hurt? Or
No,
what?
no, I said, Jonathan, you were asking him a question. I had caught only part of it.
Oh, it was like a whole thing though, my man. Troy had asked a
No, no,
question.
I had heard about the tensors and the training and this and that, but what was the last part of that question?
If I do remember correctly, I believe the last part of the question, which is Troy's question, he essentially asked that if um, when we're training our model, if the output, because you know there's back propagation. So essentially, if it keeps getting better and starts to plateau, meaning that it's no longer having meaningful gains towards the correct answer, he asked if that's the same as overfitting. In my answer, I said I think the correct answer is possibly, because I think there's more variables to consider. But I don't know if you had a definite answer to that.
Overfitting, that exact term I'm not too familiar with. If it
Mhm.
goes along with overtraining, then yes.
Okay.
Because there's a point in which the model will just stop learning. Like once you find the right thresholds and the epochs and this and that, you will see the ramp up, the learnings, and then it'll just start to degrade over time.
Okay. So then, do you feel like the answer then to Troy's question is always or possibly? Or would you not feel
I'm
comfortable specifically answering that at the moment?
I can say from my own trainings that I've seen that once you overtrain, it's just nothing. You're not getting any benefit. You're just going backwards.
The reason I said possibly, and I may be overthinking it in the sense, is because even if you plateau, it doesn't mean you're getting closer. So you can plateau with bad results. No, yeah, exactly. No, I think I would stand by my answer, especially with the way that you described it, Mike. I think is fair to say that because you know, what if your goal is zero point 0.8, right? You're at zero point 0.2, and this is just a relative, you know, relationship, and you've plateaued at zero point 0.2, you know, and then 2.1, 2.11, you know, whatever it is, it's definitely not overfitted. You just plateaued. It's just not a good weights and balances at that point.
Correct. You can think of it like when you're training in sports.
Mhm.
All right. There's only so far you're going to get, and then it's just you hurt yourself. Up at that point, there's no gains, there's no nothing.
Hmm. Yes, I agree. And but I would also say that's what the use case now where someone has already been exceptional, right? Because you're talking about like someone that's like good in their field and they're like, okay, you know, if you train 4 hours a day, there's no, and it's good, training 8 hours a day now is just going to lead to potential injuries, right? Is that essentially your analogy?
Well, the training is done why? So we can lock in that model, right? So we have our data sets that we did commit the training on, and then we see it, and we are doing this to find the optimal state. That yes, this ma machine is learning and it has learned, right?
For
We have
for a
reached this.
random population though, right? So you've got your training set, and if you train too much for your training set, then your random population all of a sudden, loses its the model isn't performing against the random set as well as it should be because your weights are adjusted too far beyond the
No, I
that
think technically, when you overfit a random set, your model is trying to behave as the random set that you have rather than the generic. So if you keep adjusting your parameters to fit the random set, it will continue to model that same random set. So basically, improves its accuracy for the random set, such that when you bring in a new data set that is not within the random set, it will not know what it will do. So that's what I believe overfitting is all about. So there is a point where your model should be able to say, oh, okay, based on what this data is, I know it's a random set, and I'm removing some random noise within this random set. This is what I should be able to model. So that would generalize based on that, neglecting the random noise that is embedded in the random set, and assume that this is the best I can get, such that when you bring in any random data to that particular model, it will be able to capture the actual data set, not the random noise that you have. It will capture the actual data set. But when your model is capturing both the actual data set and the random noise, then you're overfitting it. That's what I think
Yeah, no,
about.
absolutely. That's definitely, a great explanation of overfitting. But Troy, did that answer your specific question though? Because great,
Yeah,
great explanation though. Either way.
you guys hit it. And Mike, sorry about cutting you off.
No, you're fine, brother.
You guys all nailed it. So I appreciate the deep dive into that. Thank you.
Cool. And then I did send this quick article I wrote that is meant for I I intended to write it for a general audience, but I don't remember the details to say for sure if you have to know the anime Hunter x Hunter uh, to get the full to get the full analogy that I was creating. But it does talk about regularization, which is essentially there's two different methods of it within the article that prevents overfitting, which is through this process it prevents overfitting. So if you guys want to read that later, if it's beneficial, let me know. If it's not, let me know. And. All right, cool. So training loop, we've kind of, I think, talked about this. I think we've kind of hit that. But then what does it actually look like? So right here, this is, this is essentially the steps of it. You can refer to this, but remember in the lab, the lab itself is going to be a walkthrough. So that's why, showing it now and then later is kind of. But here, like it shows you how to do the forward pass, which is actually the data right in the model, having this output here. How you're going to calculate the loss. This is just one example of how to do it. Back propagating, just going back through it again right here, and then updating the weights. But like I said, I just feel like out of context, this isn't going to give you much value. But I think once you get to the lab, everything will be more clear. This is just explaining these. But for now, once again, here's just another code snippet that you could do. But this is a working example if you wanted to see it. But once again, for now, I would say it's okay if we skip, especially just based on time constraints. But you can use this as a point of reference if you do need additional help with your lab. And then if you wanted to understand it, I think it's more important to just talk about the concept. Like I said, this is the other one, I'll show the code. But here it contain 60,000 training images of handwritten digits in this example. Just know that the network is taking the inputs. Here it's obviously a flat input then. Oh yeah, it says right here, flatten. It's passing it through these hidden layers, right? 128 and 64 neurons, and then it's outputting 10 classes. So if you guys want to see what that looks like, it'd be right here in the code. And then you'll get a result after 3 epochs. That's 3 times through. You should see 95% plus accuracy. The model has learned to recognize handwritten digits. All right. Well, that's just, like I said, I think it's better to kind of go through that process again, just so you're better prepared for the lab than seeing the specific code. Key concepts, remember hyperparameters, what you configure, parameters, the weights and balances that the, I don't want to call it AI, it's not even AI at this point, that the machine learning's, learning from, it's changing. There's batching, which is processing multiple examples at once, faster and more stable than one at a time. That's through the GPU. There's epochs, which is one complete pass through the entire training set, usually trained for many epochs. And then learning rate. This is what we were referring to in the sense of plateauing or not. How big of a step to take when updating weights. Oh, I apologize. That's not correct. It's how much to adjust it. My apologies. So too high equals unstable. Too low is slow training. This is one of the most important hyperparameters to tune. Does anybody want to read these common pitfalls?
Common pitfalls and solutions. Problem, runtime error, shape mismatch. Solution, Check tensor shapes at each step. Use dot shape liberally. The input to each layer must match the layer's expected input size. A problem. Loss is nan or increasing. Solution. Your learning rate might be too high. Try LR equals 0.0001 instead of LR equals 0.001. Problem. CUDA out of memory. Solution. Reduce batch size or move to CPU by removing .2 CUDA calls.
Yeah, so it's just if you happen to run into these problems, especially remember you're going to do the lab, which is going to hold your hand, and then you guys are going to just play with things, and then you may run into these, and that's fine. But just know you can come back to either one of these lessons and see how to get back on track. But that's the whole point, though, is to run into these, to be experienced or be exposed to that. Here are some practice exercises you can do. We're not going to do them right now, but if you'd like to do them, if you finish early or just on another day, go back through both of these lessons, had them. And then this is just the same thing. I think now we've kind of beat this to death. Data, tensors, reshape for the network, forward pass. You check the loss. All right, back to say, hey, how much do we need to change it, and then repeat. And that happens however many times it needs to happen. I thought I had deleted this. I'll update the thing. This is not accurate. There's no lesson 3. And tomorrow, I'm not even quite sure what it's about. So originally I was going to write a lesson 3, and then I forgot to delete this. There's also resources here. Neural network tutorial, the MNIST dataset, which you guys can utilize, and then activation functions explained if you just want a little bit more. Actually, let me double check this real quick. Yeah. I mean, I don't know how much value this will give to you. You can check these non-linear ones, especially the ReLU, and let me see if there's another one that may be. Our ReLU's the updated actually version because it uses randomized. But I don't think it's going to give you too much value at your stage, but do read the other docs. It'll definitely be beneficial for you to have a more in-depth understanding. Like I said, here we're just kind of touching the surface of a concept that sounds basic, but then once you start getting into it, it's going to get crazy fast. Especially without the proper, if you haven't had extensive AI introduction before. But for now, that's essentially what I'm going to do for you guys. What you're going to do, how many people do we have here today? 2, 4, 6, 8, 9. What I would like to see from you guys, I know a lot of you are lone wolves, but I would like to see you guys break into to 2 groups. So I'm just going to open up 2 rooms today. Sorry. It's not necessarily like, oh, hey, you're going to need each other to complete the lab. But I think if you guys work together, you can help answer questions if they arise. And then, like I said, when it's time to break things, I think you guys as a group can potentially, once again, help understand what's breaking and why. And I've noticed, like I said, I know you guys do like working alone, but I also notice a lot of times that we're discussing things. Everyone usually has really great insights, great alternate perspectives. So I want to see if you guys are able to do that in your group without me being here, or whatever instructor. Because that is, even just the discussions that you guys have is like literally the point of being an engineer. Whenever you're at a company, like that's like the point is someone brings something up and you say, what about this? Did you think of that? Actually, wait, whatever it is. So, I want you guys to do it. Just talk about it. And then, so for the assignment here, you can just experiment with architecture. These are just examples of what you can do. Experiment with hyperparameters and then create a comparison report. Document your results, configure whatever, and then there's bonus challenges here. Like I said, I really want you guys to really just get your hands dirty. You liked it last week, so let's see what you can do in the sense of actual learning within this smaller area. For the lab of building your first neural network, the only thing that you really need to know for sure before I let you guys work together on this, is you definitely need 3.8 or higher. In VS Code, Python extension, which you kind of need that, but you do need this one. If you don't have the Jupyter extension, your Jupyter file is like probably not going to do anything, I think. So just ensure you have the Jupyter extension. You guys more than likely don't have that. And then you already have terminal access. That shouldn't really be there. Yeah, I mean, that's practically it. Before I put you guys in groups. Oh, also don't forget the, if it's not in here, it better be. Yeah, don't skip this step. Do not skip this step. The virtual environment is very important now, more important than it was before. Let me stop sharing and end this real quick.